Hi, I'm Robert Burgess.
I'm Samuel Lee.
And I'm Eric Estes. We're all senior electrical engineering majors at Texas A&M University, and our project is to create a dynamometer for polymorphic antennas.
Our objective for this project is to build a dynamometer or test bench to test the detuning and fluid compensation of flexible antennas. Possible applications include flexible wings on aircrafts, astronauts' spacesuits, or putting antenna on any flexible surface. Bending an antenna changes internal properties and performance. This detuning reduces range, power, and signal-to-noise ratio at the specified frequency. Resonant frequency is determined by both antenna length and permittivity. As length increases, resonant frequency decreases. As permittivity decreases, the propagation speed and the resonant frequency increases. So, in order to correct antenna detuning, one can lower its dielectric as it bends and raise its dielectric as it unbends. Here's a basic flow chart of our project. We created the test bench in a modular fashion, integrating the modules one at a time. We will briefly cover each module and highlight certain areas of our project. Here's our final patch antenna on PDMS substrate with a copper ground plane. The two capillaries running left to right through the substrate are clearly visible. Also, on the left side you can see the strain gauge sensor used to detect how much the antenna is bending. Changing the material inside the antenna's capillaries shifts the resonant frequency as shown in the simulated VSWR plot above with water and PDMS. The simulated shift was about 32 MHz. Strain gauge sensors change resistance as a function of the mechanical strain on the sensor. By connecting the sensor to a Wheatstone bridge, we can essentially convert this resistance to a voltage. We can then use the voltage to quantify how much the antenna is bending. Using conductive epoxy, we attached leads to the sensor's terminals.
The Wheatstone bridge is balanced to produce the largest range of possible voltages. Since the strain gauge resistance is approximately 350 ohms, the other side of the bridge circuit also has a resistor of around 350 ohms. The op-amp is a simple inverting op-amp with a gain of 1000. This output voltage will be fed into the data acquisition board, or DAC, which will enable us to control the pump. Here is a PSpice schematic of our relay circuit. By turning the relays on and off, we can control the actuator and the pump in both forward and reverse directions. This is our final circuit on a breadboard. Here you can see the relays are on the right and the Wheatstone bridge and op-amp are on the left.
We created a LabVIEW VI to control our system logic. The VI has two modes, manual mode and demo mode. Manual mode allows the user to manually control the actuator direction, while demo mode has a user-defined loop time that sends the actuator up and down for a certain amount of time. The sensor data is taken from the op-amp, stored as a dynamic array, then converted to a waveform. From this waveform, we can calculate the slope of the sensor data, telling us the direction and rate of bending. Based on this information, we can correctly control the pump. Here's our final LabVIEW GUI. The user can choose demo or manual mode to control the actuator. The user can also set the sample rate and window size, affecting the system's response time. The sensor data is graphed on the right, and the sensor voltage and slope is displayed on the bottom left. There are also 4 LEDs which constantly show the status of the actuator and pump. This is our final fluid network. The left photo is our voltage-controlled peristaltic pump. On the right, you can see the blue-dyed water being pumped into the substrate's capillaries. Here's our final test bench with the DAC, breadboard circuit, fluid system, and antenna with capillaries all connected successfully. This is a video we took of our fluid system working. At this point, we were almost ready to collect data.
Here's our entire test bench for testing bending antennas and high dielectric fluids. Right now we have demo mode set up on the GUI so the actuator will go up and down for 3 seconds. So if you look right now, we have a sensor on our patch that's detecting everything, and the DAC is going to control the pump and have it go in and out depending on the sensor data. So right now there's blue fluid in both capillaries, and as the actuator goes up, you're going to see red fluid or clear fluid come in this way and clear fluid come in from this direction. So starting demo mode, see the fluid pumping in, and then the blue fluid is going to go back as the actuator goes back down.
Our test bench was successful in autonomously correcting for detuning in polymorphic antennas. Here's a video we took of our test bench working in demo mode while connected to a network analyzer. So this is recording just a continuous run in demo mode. It's just pumping up and down autonomously right now. So right now we're seeing about a 5 MHz change, which is less than the 8 when you see that when it's bending. So if you were able to calibrate it more and get more reliable sensor data, you could probably narrow that number down even further.
Here's our observed VSWR plot and Smith chart with our patch antenna unbent with air inside the capillaries. The frequency is 1.019 gigahertz. These two VSWR graphs show the difference between capillaries completely filled with water, which is on the left, and filled with air, which is on the right. Using water, we measured a total fluid compensation range of 51 megahertz.
Thank you for watching our presentation. We would like to issue a special thanks to Dr. Gregory Huff, Stephen Lawn, and Frank Drug.